So the question which we're going to be doing today is 2008 step 3 question 13, because I feel like this question is a good introduction to stats, because a lot of students when they do step don't really like doing stats questions. And this question actually doesn't require much in terms of content. So there's a lot more emphasis on problem solving in this question. And there's also some stuff at the end which we can explore if there's time. So the question's about having n strings and you're just picking the ends at random, and then you're tying those, like the two ends which you choose, together. And if you pick two ends which aren't from the same string, then you'll just tie them together and they'll make a longer string. But if you have if you pick two ends which are from the same string, then you'll tie them together to make a loop. And this question's about exploring how many loops do we expect to get. Okay, so I'll just write down a brief summary of what I just said. N strings, picking two ends to tie. If they're from the same string, then we make a loop. If they're from different strings, then we get a longer string. Now, looking back to the question, the first thing they actually ask us to do is to find the expected number of rings created at the first step. And that's something which step questions do a lot, because this is really different to what you'll find in A-level maths. Like you won't really find questions like this in further maths or A-level maths. So they usually start off with something a bit small and guide you through the question. And in this case, the guidance they're giving is to consider what happens on the first step. So let's introduce a variable. Let's say let x1 be the number of rings created on the first step. And what we're asked for is the expected value of x1. And as a brief reminder, expected value of a variable, so let's say the expected value of x is the sum of the probability that the event occurs multiplied by the value of that event. So in this case, it'd be, we sum over each case as well. So in this case, E of x1 is equal to 1 times the probability that we get one loop, or I say ring, plus 0 times probability we get no rings. And simplifying that, we would just get a probability of one ring. Now, to find this probability, we can look back at how we get a ring. So that's if we pick two ends from the same string. Pick two ends. Now, the choice of the first one doesn't matter.
Mm. Mm.
Can you see why?
Is it because each end would have like the same probability? I don't know how to really explain it, but
It's thinking about how they're the same is a good idea, but not necessarily the probability of choosing each end, but what happens once we've chosen an end? Like we'll be picking a second one, but why would it not matter what the first one is? I think maybe I'll draw some strings. Let's say like we picked this end, then the probability of getting a loop is essentially just the probability of picking. I'll use a different color. We can only get a loop if we get this guy, and all of these ones, they won't help us. Well, if we picked a different end, let's say this guy, then we again only have one other end which will give us a loop, and all the others will just do nothing. So for whichever first end we pick, the second one will only give us a loop if we pick it on the same string, and that doesn't matter which. It doesn't matter which end we pick on the first one, because it's only that string which will work. And you can think of this as pretty much all the strings are the same. It's just we're thinking of a string as just a line with two endpoints. So in this case, did you all get that? If there's, I can explain again if you need it. So this was just a case with three strings. Here we have n strings, and we just pick our first end to be whatever we want, and then let's see. I'll write once we've picked our first end. Only one end will give us a loop. So since we have an equal probability of picking each end, what do you think the probability of getting a loop is then? It might be easier to think about a small number of strings first, like this case, for example.
You can also type in the chat if you want to.
Yeah. Like, oh. Why 1 minus 1 over 2n minus 1? This is the case of when we do make a loop, by the way. Oh yeah, then it's right. So not being a loop is 1 minus 1 over 2n minus 1, and making a loop is 1 over 2n minus 1. And you can see that by if we go back to the 3 strings we had before, we've picked this end, so we can't pick it again, obviously. And then now we want this red one, and we have the choice of this end, this one, this one, this one, and this one. So we get so this is 1 over 5 in this case. And if you think about the case with n strings, then we block off our 1 here, and this string will contribute only 1 end we can pick from, and then all the others will give us 2, and there's n minus 1 other strings left, so we get like we have 1 plus 2 times n minus 1 equals 2n minus 1 and to choose from, and only 1 works. So new loop is 1 over 2n minus 1. And if we go back to the expected value of x1, which we had before, if you remember, that's expected number of loops after the first step. So e of x1, I'll just write that's just equal to 1 over 2n minus 1, which is the first part of the question done. Okay, now the next part of the question is hence obtain an expression for the expected number of rings created by the end of the process. And since it says hence, we have to use what we've just done. Sometimes you get questions which say hence or otherwise, but pretty much almost always you have to use the part which you did before. So in this case, since we worked out what happened on the first step, I think it's reasonable to try find what happens on the kth step. And so we need to imagine what the situation is like for the kth step. And I think the easiest way to do that is to think about what can happen after the first step and see how that relates. So after the first step, we either have a loop and n minus 1 strings, or we have a longer string and a longer string which we made by combining 2 strings and n minus 2 other strings. But if you remember from before, we don't really care about the length of a string. We only care about tying them together, like, or tying it to itself. So the length of a string doesn't matter. So we can think of this long string is essentially just the same as these smaller ones. So we can just say this is n minus 1 strings. Now, in this case, we just have the only difference now between these 2 cases is that this one has 1 extra loop, and this one, because they have the same amount of strings as each other, So if we were to do the same thing on the second step, that loop can't contribute anything. So we can just repeat the reasoning we did with x1 on something called, like, if we had x2 for the second step, then we'd get exactly the same thing. So we could say e of x2, which is expected number of strings in the second step is 1 over, well, can you guess what it is? Because I want to see if you understood that, because this is like the main part of the problem.
Yep. Here we just need the probability that you get a loop after doing the second step. We're not asking about what happens in the first step, because either way you still have n-1 strings. So just think about the second step on its own without thinking about the first step.
Yeah. So the key idea.
Yeah, we've got 1 over 2n-3 in the chat.
Yeah. I'll just explain it again, because I think there's some people who didn't understand it the first time. So I think it's worth going over again. So the key idea is a loop which has been made on the first step won't contribute to making another on the second step, because you can't tie together, like the problem doesn't let us tie a loop with a string, and that wouldn't really give you another string or a loop. So we can think of the second step as, like, in these two cases we have only n-1 strings in both, so we can think the second step as just starting with n-1 strings, and that's essentially what we did for the first one, but instead of having n strings, we had n-1 now. So in the same way, as expected value of x1, we have e of x2 equals 1 over, and instead of n this time, we have n-1 here. So 1 over 2 times n-1 minus 1, and that's 1 over 2n minus 3, as someone in the chat said. Does that make sense now? Okay, that's good. And now we can say on the kth step, we have, if we define similarly e of xk, which is an expected number of rings created on the kth step, that's 1 over 2 times n minus k plus 1 minus 1, and that's 2n minus 2k plus 1. And you can check, you can see that works with k equals 1 and k equals 2, which is always something which is worth checking in your, well, it's worth checking your algebra when possible, especially when it doesn't take that long. Now, the other question to ask is, how many steps will there be overall? You can have a think about that and see if you can come up with the answer and type it in the chat or something.
Yeah, you might want to think about what happens to the number of ends that are left at every time that you do a step.
Yeah. This is steps overall. Like eventually we'll get to a point where we can't create any more loops or we can't tie together any more strings. Because we've run out of strings, I guess. Like, because of course, once we make a loop, we can't tie that anymore. Okay, yeah, end steps. Nice. And the reason for that, again, we can split into cases. So if you think about the first step, we either make a loop, have n-1 strings, or we make a big string and n-1 strings. And either way, if we tie together, if we make a loop, then we lose that string because we can't use that anymore. But if we tie together two strings, then those two strings become one string. So in either case, we reduce the number of strings by 1. And since we started with n strings, we'll have n steps. Okay. Now we have pretty much everything we need to answer the next part of the question, which is what's the expected number of loops overall? So let's call this x. And then we want to find the expected value of x. And if we think about the x1s, the x2s, and x3, x4, x5, x6, and all that stuff, then the number of loops created overall is the number of loops created on the first step plus the number of loops created on the second step all the way up to the nth step. And then we have expected value of x is equal to expected value of x1 plus expected value of x2 all the way up to xn. And then we have this thing called the linearity of expectation, which says if we have the expected value of a sum of different things, then that's equal to the expected value of each of them added together. And I won't be able to show you a proof of that now, but you'll see this in first year probability. And it'll be it'll be there in elbow mass, but I don't think they'll pay much attention to it. But this is like one of the most important things about expectation. Anyway, if we put in the results we had from before, we get 1 over 2n minus 1 plus 1 over 2n minus 3 all the way down to 1 at the end. And that's the expected value of x. Okay, now the next part of the question says, find also an expression for the variance of the number of rings created. And as a recap, the variance of some variable x is the expected value of x squared minus the expected value of x, and then squaring that. And in this case, well, I'll say what this is. The expected value of a variable squared is the probability that it occurs. Like summing over the probability that an event occurs and multiplying it by the value of that event and squaring it from I equals 1 to n, which is like all events which happen for that variable x. You probably use this when calculating things like standard deviation in further maths. So in this case, we want to use something similar to the last thing we did. So we can say x is equal to x1 or 2xn. And we hope for something like, well, we have this is true. And it'd be really good for us if this is true. And unlike expectation, the variance isn't necessarily linear. But it is linear if the variables are independent of each other, because they won't affect each other then. And this is also just like the linearity of expectation. It's also in first year probability, but I'm pretty sure you encounter it in further maths as well. Like as a side note, I think an example which I got when I was in year 12 was the variance of 2x is equal to 4 times the variance of x. The variance of x plus x is equal to 2 times the variance of x. Well, that's it. We'll call them x1 and x2, where x1 and x2 are observations of the same distribution. And that's because these two are independent of each other. So we just add up the variances because they won't affect each other. But this one, multiplying by 2 isn't the same as adding 2 independent things, because if you think about like the graph of x, the values which you can observe can be have a wider spread, I guess. But yeah. Now, what we want to show is that x1 to xn are independent. And if you remember, we defined xk was number of loops created on the ket set. if you remember, creating loops on previous steps didn't affect what happens on later steps because we still end up with the same number of strings, and we can't use the loops again once they've been made. So since previous loops can't affect the loops which are going to be made next, that means that they're all independent. So that means we can use that. That means you can use that formula for the variance, where we just add up from x1 to xn, which is a lot easier to calculate because we already have the expected value of x1. So I'll calculate the expected value of x1 squared, which is just 1 squared times the probability loop on kth step plus 0 squared times probability no loop on kth step, which is 2n minus 2k plus 1, like before. And that means that, I'll just go through the calculations. So the variance is this by definition, and then you get 1 over 2n plus 2n minus 2k plus 1 minus 1 over 2n minus 2k plus 1 squared, and that's 2 times n minus k over 2n minus 2k plus 1 squared. Now, we can just put all these in, and we end up with the variance of x is 2 times n minus 1 over 2n minus 1 squared plus 2 times n minus 2, 2n minus 3 squared, all the way down to, when n equals k, we'll just get 0. So I'll stop at the second to last term, which is when k equals n minus 1, and we'll get 2 over 3 squared. And that's the variance. And I'd say that's probably the most detailed and difficult part of the question. So the last part is just wait, did you all get that? Because I can explain again, of course. Okay, that's good. Now, the last part of the question is, given ln 20 is approximately equal to 3, and that 1 plus 1/2 plus all that stuff is approximately equal to ln n, determine approximately the expected number of rings created in the case n equals 40,000. Now, we just put in 40,000 in our formula. So expected value of x is 1 plus, it was 1/3 plus 2, 1 over, let's go back, to 1 over 2n minus 1. So let's say 39,000, well, 79,000. Okay, but I think very easy if we just work with n for now, for the algebra, instead of writing something so big. Now, we have 1 plus to 1 over n is approximately equal to log n, oh, not log, sorry, ln. n. And we want to determine an approximate value for this. So it's reasonable to try and use this. But what we have here is only the odd denominators. So we can't directly use this. So we need to do some algebra to find out how to express this in a form which looks like this, so we can use this approximation. And I think this is a really common technique when it comes to handling series, because we can think of 1 plus up to 1 over 2n as the sum of the odd terms plus, let's say this is odd, and the sum of the even terms. Let's put these in brackets to separate them. And once we do that, the key thing about the even terms, so I'll just quickly write the odd ones, is that we can factor out that 1/2, because we know that each of the even terms will be divisible by 2, like their denominators. So we can just take that out and we'll end up with 1 plus 1/2 plus all the way to 1 over n. And now this is in the form we want. And the thing on the left-hand side, this is also in the form we want. So we can now just apply our approximation. And we end up with ln 2n is approximately equal to 1 plus 1/3 plus, so 1 over 2n minus 1. That's our odd terms, plus 1/2 ln n. And rearranging, you get 1 plus 1/3 plus 1 over 2n minus 1 is approximately equal to ln 2n minus 1/2 ln n. Now, for n equals 40,000, you then get e of x is approximately equal to ln 80,000 minus 1/2 ln 40,000. And here we just do a calculation with log rules, because we expect to get something which will use ln 20 is approximately equal to 3. So I think the best thing to do here is to just keep simplifying and just hope you get something which looks like what we've been given. So 1/2 ln 40,000 is equal to this is ln square root of 40,000. And you might recognize that as 200 squared. So we get ln 80,000 minus ln 200. Then that's ln 80,000 divided by 200, which is ln 400, which is just 2 ln 20, which is approximately 6. And that's the question done. And I think I'll say that's kind of a really small number. Like, you start with 40,000 strings and you only expect to make about 6 loops, which shows you how slow this thing is. But interestingly, in this formula, ln 2n minus 1/2 ln n, if we take that to infinity, like, that would actually diverge. Like, as n goes to infinity, e of x will tend to infinity. But as you can see, it does that really, really slowly. But yeah, that's the end of the question. Did you all understand that last part as well? Okay, nice. Since there's some time left, there's probably like, I think there's like another 25 or so minutes left. There's still some things which, there's still some related things which you can look at. And I think I'm gonna have to make a new Jamboard. So one thing you might be wondering about is that in a, like that approximation, 1 + 1/2 plus blah, 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 plus 1/n, approximately to ln n. You might be wondering, how did someone come up with that? This is called the harmonic series, by the way. And there's some interesting things which you can see from this approximation. While it's not obvious that the harmonic series, like how the harmonic series grows, like does it reach a bound or anything like that, on how quickly it increases and things like that. This side tells us that as n goes to infinity, 1 + 1/n, that also tends to infinity. But it tells us that it happens really, really slowly. Like if we do something like n equals, well, we saw just then, for n equals 400, 1 plus is going to be about 6. And for n equals 20 to the 20, which is probably something, it's much more than a billion terms. For this n, you only get about 60, which is really, really small compared to the amount of terms on this side. And as for how to show this approximation, it's useful to think about a graph. So let's sketch y equals 1/x. No, not infinity there. X. This is y here. Okay. Now let's just call this point 1. One thing you can realize is if we draw a rectangle here, match it up with the curve, then we'll get a rectangle of height 1 if we, and width 1 if we stop at 2. And then if we create another rectangle here, then this has height 1/2 and width 1. So this is area 1, this is area 1/2. If we do the same thing here, we'll get area 1/3, height 1, because the height is 1/3, the width is 1. And we can keep doing things like that. You know, let's just say we stop at some point n. That's area 1/n. So there's a few observations we can make here. First, the total area of the rectangles is 1 plus 1/2 plus 1 over n. And the other thing to realize, I'll call this an important observation. How does the area of a rectangle compare to the area under the graph? Well, I'll give a hint by shading. This is the area under the graph, and then in the rectangle we have this as well. Yeah, the rectangle's all that's a good. I guess that's anticipating what I'm going to do next. I was looking for something a bit more basic, like what Jesse said. The area of a rectangle is more than the area under the graph, because the rectangle has the red part and the blue part, but under the graph we only have the red part. So the rectangle has more area in it. And that means we can say the total area of the rectangles, which is 1 plus 1/2 plus 1 over n. And that's the series we're looking for. That's the series we're trying to study. That's bigger than the area on the graph from 1 to n. And we know from calculus that this is the integral from n from 1 to n of 1 over x dx. Now, this integral, you've probably covered it in class. This integral is just ln x from n to 1, which is ln n minus ln 1, which is just ln n. So we have one plus 1/2 plus 1 over n is bigger than ln n. And while like this is a useful statement, it's not quite the approximation we had before, because it could end up being a lot bigger than ln n. So we need to do a bit more than this to establish the inequality. And to do that, I think it's got to take another look at the graph again. Call this point n. This is x, that's y. This is y equals 1 over x. But this time, instead of starting our rectangle from here, we're going to start from here and go back here. Then that's the triangle. That's a rectangle with width 1 and height 1/2. I'll draw back this one. And then for this guy, do the same thing. We've got height 1/3. And this guy got the same. And so on. Okay, so the total area of the rectangles this time is 1/2 plus 1/3 plus 1/4 to 1/n. And what can we say about the comparison of the area? How many rectangles and area and the curve compare now? I'll use the colors again. Oh. Yeah, the area of rectangles is less. Let's use the red here. And we'll just dot this line. So this time you can see it's less than the area under the curve. So like last time, I'll go through this a little more quickly. We end up with this is less than area under curve from 1 to n, which is again the same interval. You can say this is ln n. And now to get this side, the left-hand side, looking more like what we had before, you just add 1 to both sides. So 1 plus 1/2 plus dot 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 plus 1/n is less than ln n plus 1. And putting together everything we've got now, we end up with ln n is less than 1 plus 1/2 plus dot 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 plus 1/n is less than ln n plus 1. And now, now we can say if n is large, like, let's say very large, then ln n plus 1 is going to be approximately equal to ln n anyway. So we have 1 plus 1/2 plus dot dot plus 1/n is not that sign. This one. It's approximately ln n, like the question gave us. Now, this is similar to something called the integral test. Which is in first year analysis. You can look that up if you're interested. We use it on the harmonic series. And from here, there's a couple of things we can do. An interesting question, I think, is, well, how close do 1 plus 1/2 plus dot dot plus 1/n and ln n get? Or we could say, or we can think of this as, how far apart are they? We know that if we consider I'll go on to the next page actually. we know that 0 is less than 1 plus 1/2 plus. So the partial sum of the harmonic series minus ln n is less than 1. And what happens if n goes to infinity? Well, we can show that this does settle to a number. What's the limit of this? You can look online. There are proofs that this limit exists. It's not much more than we've done here to show that. And we call this limit gamma. And it's known as Euler's constant. Like the same Euler who came up with E and all that other stuff. But keep in mind, E is Euler's number. Well, this is Euler's constant. And its value is about 0.577, some other stuff. So between the bounds 0 and 1, as we had before. And this constant, it's quite important in maths. You've probably not seen it before, but it appears in number theory, I think complex analysis, some other stuff, which you'll see as you study more maths at university. If you've heard of the Riemann hypothesis, it's related to the Riemann zeta function as well. And there's like there's a lot of questions which are still open about this number. We know that E and pi are irrational, which means they can't be expressed as a fraction with E and pi can't be expressed as a fraction with integer numerator and denominator. But for gamma, it hasn't been proved yet. Which is, I'd say it's quite interesting, given that it's a number which we've known about for a few hundred years, but still don't even know something as basic and important as this. But anyway, yeah, that's the end now of all this extra stuff to do with the question.
Great, thanks. It's a challenge to our participants to go and try and prove that.
Yeah, if one of you prove it, you'll probably be remembered for at least a few hundred years.